I guess start broadcast. There you go. All right.
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon. Welcome to the webinar on PTC Mathcad Prime 3.1. So here's how you can participate today. You see the little arrow. You can open and close your panel on the right there. Number two, you can view, select, and test your audio. Number three, we're not going to do that, but you can submit your questions. All participants are in a listen-only mode. Please submit your questions, and we will get to as many as possible at the end of the presentation. My name is Joe Ferret. I will be your moderator today. I am the Mathcad Support Specialist at Barry-Wehmiller International. Tim Bond from PTC. He's a Mathcad Application Engineer. He will be our presenter today. Here's a quick breakdown of our agenda for the webcast. We'll do a quick intro to Barry-Wehmiller for those who have not attended one of our presentations before. And then Tim will go through a quick presentation of PTC Mathcad and perform a live demonstration for everyone. At the end, we'll answer as many questions as possible. If we do not get to all of them, we will follow up to everyone on the webcast with an email. So, dollars in revenue. So we're all here for PTC Mathcad, but Barry-Wehmiller is much more than just a PTC partner. We are a total solutions provider helping manufacturers across the entire product development spectrum. So we have expertise in putting all the pieces of product development together. From PTC product solutions to engineering, design, and development, onshore and offshore, to ERP enterprise systems, to even PLM solutions. We have an unbelievable PLM team here at Barry-Wehmiller. So just a quick overview of Barry-Wehmiller. As you know, we're a PTC partner. We're one of the leading training partners for PTC. We have 7 training centers across the United States, and we're in the process of opening 3 more. We have application engineers that teach our training classes. All of our engineers have over 15 years experience using Creo and Creo in real-world and classroom environments. Here are a few of our BWI customers that we've worked with in the past. We understand that small businesses have the same issues as larger companies, so we want to iterate that we work with small to medium-sized businesses on all PTC products. I'm going to turn over the presentation to Tim Bond now.
Great, thank you very much. As soon as I get control here, I can get going. So my name's Tim Bond. I'm an application engineer at PTC, and I'm here today to talk to you guys about Mathcad Prime 3.1 and its new integration with PTC Creo Parametric 3.0. So Mathcad itself is a digital engineering notebook that's going to allow the end user, the engineer, to analyze, solve, document, and share their engineering calculations and design intent. In Mathcad, we do that through the combination of text, images, graphs, and a live math engine. The math engine can compute numerically and symbolically, and I'll show you that a little bit as we get going here. Joe, if I could just have presenter rights, that'd be great. There we go. So you should be seeing my screen here now. So Mathcad on an enterprise level is going to allow the company to retain intellectual property. We do that through the use of templates. So at your company, you have standardized calculations, best practices within your calculations, and those can all be stored in Mathcad worksheets and in templates. So a template is something that you build once, you save it, and you can reuse it for design iterations down the road. When everything is documented well in a Mathcad worksheet, it's saving that intellectual property that when you're using other tools, for example, if you're using a coding language or maybe an Excel spreadsheet to do your calculations, the programming language is very hard to learn. If you open up someone's Excel worksheet, it may be difficult to understand what's going on, but in a Mathcad worksheet, it's text, it's natural math notation right in front of you, so that if a new engineer that's come on board to your company opens up the Mathcad sheet, they can very easily just read the document and understand the calculations that's happening. On an individual engineer level, I've said it before, the documentation aspect and the natural math notation, the unit management system that Mathcad offers, allows an engineer to effectively do his job quicker and document it and share it with his or her manager, or the fact that you have the document there, send it off to a third party to verify any requirements that you may be governed by. So that's a little bit about Mathcad, and Mathcad Prime 3.1 has a new integration with PTC Creo Parametric 3, and we're calling it the Engineering Notebook powered by PTC Mathcad. So Creo itself doesn't have a great way to document a design, and at PTC, obviously, we own Creo and Mathcad, so with this latest release, it's going to allow you to better connect your engineering calculations to the relevant CAD models. And this integration was designed around 3 use cases. The first is simply documenting design intent. So in this integration, again, I'll show this here in a couple minutes, you can embed a Mathcad worksheet within a Creo model. The Mathcad worksheet could simply be a 5-page document. Maybe it's from the manufacturer that the part has come in from, explaining what the part is. Maybe it's some design notes that the CAD engineer jots down as he's designing that part, so that when he passes it on to a colleague or his manager opens it up, the manager could open up the Mathcad worksheet and kind of read through what's going on in the CAD model. Why was it designed this way? The second 2 use cases, analysis-driven design and verification and validation, speak more to actually sharing data between Mathcad and Creo. I'll talk about that in a second. So the capturing design intent inside your model, like I said before, we're going to take a Mathcad worksheet and embed it in the Creo model. Once it's embedded, that Mathcad sheet travels with the Creo model wherever it goes. If you're using a PLM system like PTC Windchill, if you check that Creo part into Windchill, the Mathcad worksheet will go right with it. If you email the Creo part or assembly to a colleague, when he or she opens it, the Mathcad sheet will be right there with it. And this is going to allow you to send design documentation with your CAD model. The second and third use cases, as I said, are about sharing data. So with this new integration, it's going to allow you to take Mathcad regions and turn them into Creo parameters. This is going to allow you to do things like analysis-driven design. So if you have a worksheet, a calculation, and the outputs of that, the results of that calculation, are the length of a beam or the diameter of a bolt or something like that, you can then push that value to Creo to actually drive the geometry. Verification and validation is the reverse of that. You have a Creo model. You want to pull parameters off of the Creo model and verify that they meet requirements. I'll run through an example when I get to the lot demonstration, but when I get to my crankshaft assembly pictured here, I'll demo this shortly. Does the crankshaft assembly displace the correct amount of air? Does the 6-cylinder engine displace the correct amount of air? Mathcad can calculate that for you. So with that said, let me exit out of PowerPoint and come into live Creo. So this is, again, this is Creo Parametric 3.0. It's date code MO30. And when you have Creo 3 and Mathcad Prime 3.1 installed on your system, on the Applications tab, there's a new Mathcad icon. This is the engineering notebook powered by PTC Mathcad Integration that I've been describing. And it's going to present the user, if you click the drop-down, with two options. Option 1 is to embed a blank worksheet into the Creo model. And option 2 is to insert a copy of an existing worksheet into the Creo model. That's what I'm going to do here. This is just, first demonstration is just a simple, straightforward example. This is one part with one helical sweep. It's a spring. And what I'm going to do here is I'm going to embed a Mathcad template for a spring design. Now you'll notice, for those of you who haven't seen Mathcad, it has a ribbon interface with tabs that you can go. So if you'd like to add a plot or edit the plot, move to the plot tab. If you'd like text formatting, document, Mathcad is a document, you can tell. It looks like Microsoft Word, except it has a math engine. It has all the standard documenting, margins, page orientation. You can choose to show the grid or hide the grid, page breaks, numbers and bulleting, headers, footers, all that kind of stuff. On top of it is the math engine. You see units are formatted to be bolded, italicized in blue. That's customizable. That's just the default. And all of this math that's shown here is live. So what this worksheet does is it's going to take inputs. So, for example, some material properties, the allowable shear stress of the material we're using, how much load is going to be applied to this spring, and it uses, in Mathcad we call this a solve block, this region here that's outlined, and what it does is it solves systems of equations. In this case, the minimize function here at the bottom is minimizing this weight function. So we're going to minimize the weight of the spring, while using Boolean operators, we're going to satisfy the deflection constraint, the shear stress constraint, the frequency constraint, and the dimensional constraint. So that's kind of what this Mathcad sheet is doing. One thing you'll notice is that the name of this worksheet is actually the Creo part with the part icon. On the Mathcad side, you have multiple worksheets open. This is unentitled. This is the spring. It gives you the...
Hey, Tim. I'm sorry, but your screen keeps on flickering back and forth between the model and the worksheet.
Huh. Let me minimize Creo and see if that stops. Apologize. Is that better?
Yeah, it also keeps it going to your home screen, like showing your home screen too. It keeps it like flickering back and forth for some reason. It seems better now.
I'm not sure why it's doing that, but I'll give it a second here. See if that is cleaned up at all.
It looks like it stopped now.
Okay. Sorry about that. So when you're working with the embedded worksheet, you have the notification here that when you're on this tab, you're in the embedded model. Also, up here on the toolbar, the save icon switches to a save and push icon. So when I click this button, what it'll do, I'm not going to do it yet, but it saves this worksheet within that model, and it's going to push any data to Creo that I've assigned. Now, I haven't done any of that yet, but ultimately, this is the analysis-driven design use case. So we have our inputs, we have our solve block to optimize our system of equations and minimize the weight of the spring, so we're using the least amount of material. And you see these three values here that I'm optimizing are evaluated down here as the optimal spring dimensions. So what I want to do now is I want to take these values that I've calculated and push them to Creo. On the Mathcad side, we do that using the assign input or assign output. So when I click on an evaluation region, I can assign that as an output. We have a master list that can show up, and you'll notice that the alias is customizable. The alias is what will become the name of the parameter in Creo. So let me finish tagging here. So these three regions, I'm going to send the value, the unit, and the alias to Creo. And I'm also going to, once I've set up the relations to drive this geometry, I'm actually going to pull back the final height of the spring, and you'll notice that goes into the input section. So now I've created my worksheet, done my optimization, found my optimal dimensions. Now I want to actually perform the save and push. I get a notification that it's been done successfully. And if I come back to Creo, you'll notice, first of all, that there's this Mathcad icon in the corner. This is the notification on the Creo side that there's an embedded Mathcad worksheet inside of the active part. So to see where those Mathcad regions that I've tagged as inputs and outputs show up, I can go to the parameters table, and with the new integration, there's the embedded Mathcad dropdown. I can see the source, whether it's an input region or an output region. I can see its value, its name, the alias that I assigned to it, and its unit. Now you'll notice that these are in feet, whereas if I come back to Mathcad, this is in inches, and millimeters. And what Mathcad does is, under the hood, when it's actually doing all these calculations, it works in base units. So the unit system right now is the US system. So for length, feet is the base unit of length in the US system. If I were to switch this to the SI system and save and push back, in the SI system, the meters is the base unit for length. So if I switch over here, now we're seeing meters. The conversion, is done automatically for you. So smart, it will convert units for you. It will let you know when your units are not compatible, and that carries over into Creo also. So now that we have the parameters here, what we can do is, through the use of the relations table, we can actually build the relations that will drive the geometry. So let's go ahead and do that now. I'll open up my local parameters to see my Mathcad values. And I want to drive some dimensions in the helical sweep, and we can see now the values that do that. And if I go back up to the part level, I can start building these relations. So one of the things that I did in the Mathcad worksheet was I optimized the diameter of the wire. So I can say that D6 is equal to the diameter of the wire. We also determined what the diameter of the spring coil should be, so I can say that the radius of that is going to be the diameter of the coil divided by 2. We also calculated how many the number of coils there should be, so I'm going to drive the height with that. So we have a height is going to be equal to the pitch times the number of coils. So there's our three optimal values driving. I then want to keep it centered around the origin, so I'll enter this relation. And like I said, once I do all those relations, I want to pull back the height of the spring. So now I'll put height of the spring on the left side of the equation, press equals, and I'll set that equal to the height of the sweep plus D6. I can check to see if I've put those in correctly, which I have. Good. I exit out of the relations table. Now, I'm presented with a yellow light and a yellow flag. The yellow light, as expected, we have to regenerate our helical sweep, so I can regenerate. And there's our new optimal spring. Fantastic. I also have the yellow flag saying I have an outdated Mathcad sheet. So let's come back to Mathcad. And on the Input-Output tab, we have the Update Input button. And you'll watch down here, the height of the spring will update to reflect what the Creo model tells it is. Great. Now this is, as I mentioned, this is a template. So the Mathcad template that before was just simply calculating the optimal spring dimensions. Now that it's connected to the CAD model, we have a spring, a 3D CAD model spring template. So the next time, maybe we're going to use a slightly different material, so it has a lower shear stress. And maybe we rethink the problem or the application, and the applied load has actually gone up 10 newtons. Mathcad, it's live. This solve block here recalculates and has new optimal dimensions. So what I can do is simply just click Save and Push. Come back to Creo. We have that yellow light. I can regenerate, and probably a little hard to tell, but that spring, we've lowered the shear stress, allowable shear stress, and we've increased the force. So that spring got a little beefier. Again, that relation ran through, and we have a new height of that spring. So we have another outdated Mathcad sheet. So if I come back to Mathcad, I can update the inputs. And come down here, we now have a 2.3 inch spring. So that is really how the integration works. This is analysis-driven design. Use Mathcad solve block to optimize the system of equations. Push your optimal dimensions back to the it was kind of just a dumb helical spring at first. I really just created one just to get the shape of the helical spring, and then I drove the helical sweep through the relations table. Now to get that yellow flag to go away, we need to push back to tell Creo that we have updated the Mathcad worksheet to reflect the latest height, and we're green light, no yellow flag. So with that, I'm going to close out of the spring and flip over to that crankshaft assembly that I had a photo of in the PowerPoint. So this, for those of you who don't know, is probably something along the lines of this is under the hood of your car. Maybe not if you're driving a new Tesla that's all electric, but if you have a gas car, this is probably what's under your hood. When you say you have a 6-cylinder engine, this has six cylinders, 6 pistons, and each of the pistons slides up and down in a cylinder. So as I mentioned before, what I'm going to do, same as before, and actually before I do that, I'm going to add some features to this model tree. Same as before, I'm going to embed a Mathcad worksheet that I've already created. There it is. So we embed it, and you'll see that we've embedded this into an assembly. So the assembly icon appears, and the name of the assembly is the name of the worksheet. Great. So let me come back to the Creo model quickly. And I said we're going to verify that the assembly meets the displacement requirement. So what is a displacement requirement? That's documented in the Mathcad sheet. So the requirements of this engine are an engine displacement between 3.25 liters and 3.3 liters, and a compression ratio between 7 and 9. For those of you who don't know, let me describe quickly what I'm talking about there. So this is the piston head that's shown in the Creo model, and what's not shown in the model is the engine block itself. So the piston, when a crankshaft rotates, the piston slides up and down. So this is the piston at the bottom, this is the piston at the top. And what happens is when it moves down, it sucks in a mixture of air and gas, and then it comes back up and it compresses the air and gas into a small area where it's then ignited and a powerful explosion is created, and it eventually propels your car forward when you step on the gas. So the engine displacement, which above is documented that it must be between these two values, is the number of cylinders. So we have a 6-cylinder engine multiplied by the volume of this space here when the piston's all the way at the bottom. So we're going to pull some values back from the Creo model to verify that that is happening. And we're also going to verify that the compression ratio is between 7 and 9. So the compression ratio is the ratio of this volume here when the piston's at the bottom to this volume here when the piston's at the top. So we'll verify those two things. And then back in Creo, what we'll do is we'll do a bit of an optimization on the surface of this piston head. So if I come into the piston assembly and see the definition of this sketch, you can see there's two values typed in there. There's a little spherical indentation. So we'll do an optimization around the surface area and the volume of that little cap there. And I'll tell you why that's important in a second. So in Mathcad, in order to know the volume of this displacement of the engine, I need to know two things. I need to know the bore diameter of the piston and the effective crankshaft radius. So I'm going to assign those as input regions. And when I save and push, those two regions will now be made available in the parameters table and for use in relations. So let's go ahead and come back in. And let's minimize this. Let's go into the parameters table. Go into the embedded Mathcad dropdown and select the assembly, and there we go. We have our two inputs. We're in the SI system, so length will come over in meters. And we see our default value of 0.001 meter. That's really just a placeholder at this point. What I want to do is I want to take some numbers off of this and drive those like I did the height of the spring. So to do that, I'm going to go to the front view. And I'm going to take a measurement. So I am going to, first of all, I'm going to hide this so I can see here. And let's take a measurement. Let's measure a distance between here and here. And you're going to say, well, what the heck is that? So I will go to the left view so you can actually see what's going on here. So this is the crankshaft. It's going to rotate around. And when this point here, the point where the connecting rod connects the piston to the crankshaft, when it gets to the top, that piston is going to be at its peak height. And when it rotates back around to the bottom, that piston will be at its bottom height, what I showed in the diagram in the Mathcad worksheet. So this distance here is half of the total distance the piston will move up and down. So I'm going to save that as a feature, and I'll call it the crankshaft radius. And that'll appear in my model tree so I can use it in the relations table. And I can unhide that connecting rod assembly now that I've taken the measurement. And I'm going to then come into the relations table to actually start building these relations. I want to look in the feature. The only thing left that I really need to know is what the diameter of that piston is. And if I click here, we'll see that D1 postfix 30 defines that diameter there. So now I have all the measurements I need. And if I sort this here, let me expand this out a bit by unit, we can see that I'm going to say that the Mathcad radius of the crankshaft is equal to the measurement I took. And then I'm going to say that the bore diameter of the Mathcad variable is going to be equal to D130. One thing I didn't mention in the spring demonstration is the unit sensitivity. So Creo, by default, in the relations table, the unit sensitivity is off, which means that this meter will not convert between meters and millimeters unless this box is checked. So we're going to check that. Mathcad is all about units, so we want to make sure that the right value that Creo is calculating in here is going to Mathcad. We'll check that those have been good. Exit out. We still have a green light because we haven't driven any geometry yet, but we have an outdated Mathcad sheet. So using that glyph as a hyperlink back, we can update inputs. And there's the 45.8 millimeter effective crankshaft radius that I took the measurement of. And it turns out the piston head has an 81 millimeter diameter. Now, we have all of the data we need from the CAD model to verify way down at the bottom that the compression ratio is between 7 and 9. Fantastic. The engine displacement is right on the money at 3.3, right on that limit. But how did we get to that point? Well, we used, so there's our values, our inputs, and we used Mathcad's natural math notation to define functions for the volumes of the cylinder, the piston head, and the engine block. And then we also calculate the surface areas, and we define, using the variables, our minimum and maximum displacement and compression ratio limits. So from all those, we can eventually come down and calculate our compression ratio and engine displacement. Now the second half of this, as I mentioned, we want to find the optimal dimensions here. This 30 and 5, we want to make sure that that volume and surface area relationship is maximized. So let's see why that's important. We'll come back to Mathcad. The goal here, as I've mentioned a couple times now, is to maximize this relationship. So in an engine, and let me come back to the diagram, at this top dead center point is when the spark plug goes off and a tremendous amount of heat is created. So at this point, we have a given volume, and there's also a surface area that contains this volume. And if you know anything about heat transfer, heat escapes through surface. So for a given volume, we want to minimize the surface area that that volume lives in. Okay? And again, this is an optimization problem. So you see, again, here's the volume and the surface area functions. And we can use, just like the spring, that Mathcad solve block, there it is again. Instead, this time we're using the maximize function. So if this was held constant, this volume up here, we want to minimize this surface area, which will ultimately maximize that value. We're going to keep in mind that we want the compression ratio and the displacement to be within those limits that are defined just above. And ultimately what comes out are two optimal values. The height of the piston cap, the height of the piston head cap, and the diameter of that piston head cap. And I give those an alias that I'd like. I can save and push that. So now that these new values come into Creo, and we see here we have a radius of that piston head cap and a height of that piston head cap. So now the only thing left to do is build the relations to drive that piston head surface. So let's go ahead and do that. Let's look in the feature sketch 4 so we can bring those dimensions into view. And then, again, come back up to the assembly level to build the relations. So I'm going to say that this radius here is equal to the diameter that I've calculated divided by 2. And the depth here, let me zoom in, the depth of that cap indentation is equal to the optimal height that I've calculated. Great. Check to make sure those are good. Come out, and we have a yellow light to regenerate. Now you'll notice in the model tree here, if I collapse everything down, that the piston head assembly is copied through a pattern 6 times. And so is the connecting rod assembly. It's a pattern. So not only is this piston head going to update to the optimal values, but all 6 are going to update. So let me go ahead. I'm going to zoom in. The changes are pretty subtle because my guess of 30 and 5 were pretty close. Let's go ahead, click regenerate. We'll notice that that got way skinnier, so let's actually come in and see what our new values are. And see the dimensions. So we went from 30 to 35.5, and that depth, remember in the worksheet it was just 1 millimeter, and we see that there. So now we have that optimal volume to surface area relationship that's going to decrease heat loss as much as possible. That heat loss, any heat that we lose during combustion is going to be a loss of energy, so we want to minimize that loss of energy so we can have an efficient engine. So now this is all set up, we've confirmed with Mathcad that our requirements for the compression ratio and engine displacement have been met, and 2, we've optimized that volume to surface area relationship of that piston head to make sure that we're going to have the least amount of heat loss as possible. So fantastic. I've showed two similar but different use cases. The document design use case kind of goes hand in hand. We have text regions. You saw the images and graphics going here. So this Mathcad worksheet, if you were to hand this to someone to open up that Creo part, say what's going on, we have everything clearly defined in this worksheet. Some text to note why we want to maximize this, what is the engine displacement, what is the compression ratio, etc. Now everything I've shown to this point has been about simply driving geometry or pulling geometry values into Mathcad. But the sheer fact that Mathcad is sending data to Creo into the parameters table, we can then use those Mathcad parameters or Creo parameters in other areas. So let's open up, this is just a simple bolt here that's connecting 2 L brackets. And you'll notice we have a Mathcad sheet embedded. So what we can do is we can use Creo Simulate. Okay, we have all of our loads and constraints defined. And I've already ran this analysis, but let's take a look at the results of the analysis. And it's coming up on my other monitor here. Let me pull it over. So we can see our volume EC stress of the bolt in the washer, and we flip over. There's the bolt in the washer, and there's the head of the bolt. We can see our displacement of the assembly. We can see the principal stresses, etc., etc. This view is obviously customizable. But why am I showing you this? So I close out and open up the Mathcad sheet. Now we're on the pipe stress assembly embedded Mathcad sheet. What we do is what I did prior to coming on today, I set this up so the bolt diameter is actually coming directly from the Creo model, tagged as an input, and there's a relation built that pulls that in. And what we do is a series of calculations. We derive, so we're given maybe in a reference book the torque calculations, and from that we can use the symbolics engine. So we have a function here, torque is equal to this mess, and we see maybe we want to solve for the force that's going to be on that bolt, so we can use the symbolics engine to solve that equation for F, and so F is equal to that, and we can then evaluate and see that force that the bolt will experience. Mathcad is not an FEA tool, but it's fantastic at solving, manipulating algebraic expressions so we can determine what force is going to be felt. Whenever you're running a simulation, you're not just picking a force out of thin air, it's calculated somehow. So we're going to send that force back that we've calculated using the preload alias to Creo. And you'll notice if I open up the loads and constraints that I've defined, the preload on the bolt is actually driven by preload from Mathcad. So it's not just send Mathcad to Creo to use in the relations table or pull the data back. It's Mathcad becomes a Creo parameter, so you can use it in applications like Simulate and other Creo apps. So with that, that's what I have to share with you guys today. I think at this time I'll pass it back over to Joe and see if he has any things to wrap up here. Joe, you still there?
Yes, I am. Thanks, Tim. I was just getting this set up. Thanks a lot, Tim. Just wanted to let everybody know that if you want to see a replay of this presentation, you can always go to the Barry-Wehmiller website at www.b-wi.com and click on the webcast tab to view a replay of this. Then you can also check out a replay of this presentation on our YouTube page. And you see the website there at the bottom of the screen there. Also, if you ever need any PTC training, we offer PTC certified training. You can browse our courses at b-wi.com/training, or you can contact our national training manager, Jason Hardebeck, and his email there is on the screen. Also, we have some classroom training coming up in June in our St. Louis Training Center for Mathcad. So if anyone is interested in these training classes, please contact our training manager, once again, Jason Hardebeck. If anyone has any questions, please feel free to submit your questions at this time, and we will answer them. Let's go back. Somebody wanted to see the link to YouTube. Okay, there's the link to YouTube once again. The first question here is, can any of this be done with the free version of Mathcad?
Yeah, so one thing I didn't talk about was how to get this. So first of all, Mathcad is on the Creo 3 M30 install disk. So it's an opt-in when you go to install Creo 3 M30. You can simply check the box to also install Mathcad. The integration itself does work with the free version of Mathcad. So with the free version, you have the ability to assign input and output regions. However, for those of you who don't know, actually here, let me actually get rid of my license here and go back to revert to the Express version. So with the Express version, Mathcad hit on me here. We have.
Do you want us to give you control back, Tim?
Oh, yeah, I kind of forgot I'm not sharing. Sure, if you don't mind, sure. So great, so I'm now running Mathcad Express. So the assign input and output is still available. If I were to create a definition region here to demonstrate these inputs, so we can assign input and output regions and pass data to and from Creo. But things that are not available are things like this symbolics here. In the other demonstrations, I use the solve block. So a lot of the more useful calculation abilities are not available. You see things are locked out here. Certain plot types are not allowed and things like that. So we have a list of it on the PTC website of what exactly is not there. But for example, if I were to recalculate this worksheet, we'd have, you get the error saying it's a premium feature. So things like that are it'll open up for you, but you're not going to be able to actually calculate anything. But yes, the integration does work with the free version, and you get the free version with a 30-day trial when you install it on the Creo 3 install disk.
Okay, next question here is, what happens if a Creo user attaches a Mathcad file to a part and the next Creo user does not have access to Mathcad? Your flicker in there, Tim.
I'm not sure why I'm flickering. Let me minimize. I think it's because I have maybe something going on in the background. So if I were to send any of these parts to a person without Mathcad, they would still be able to open the Creo part. They would see that glyph there in the corner. But what they wouldn't do, and now as I went through the demo, you saw the light change to yellow, and you saw that yellow flag change. Actually, I'm going to come back into spring. What actually happens there is in the parameters table, when anytime those lights appear are when the value and the Mathcad value are different. So a yellow flag will appear when the height of the spring, the Mathcad value, and the Creo value don't match. So will they be able to open the Mathcad file if they don't have Mathcad installed? No. But any data that was sent to Creo, any of these values will still be there. They just won't be able to change. Well, they won't be able to see the Mathcad worksheet to actually change those values to save and send a new iteration of the design. But yes, the Creo part and assembly would open just fine.
Great. So next question is, my Mathcad application is grayed out. We have Mathcad licenses. Do I need to pull the license at launch of Creo or do something else?
Okay. Well, I think what they're saying is this application tab is grayed out, which would mean that they either don't have the correct Creo date code installed or they don't have Mathcad Prime 3.1 installed. You do have to have parametric 3.0 date code M030 and Mathcad Prime 3.1 on your system, and this will appear, not grayed out. The second part of that question is, I believe he was asking, is the Mathcad license pulled as soon as the Creo part is opened? And the answer is no. So if I were to just simply open up this part, I'm not launching Mathcad unless I actually click on this button to get to Mathcad. So if I click on this button and Mathcad is open, then yes, I would be pulling a Mathcad license. But if you're simply just in the Creo part, the fact that there's a Mathcad worksheet embedded doesn't mean you also are pulling a Mathcad license.
Okay, next question in here is, how easy was it to embed the spherical cap into the image into Mathcad?
Very easy, just copy and paste.
So the next question is, the example millimeters was in Mathcad, changed to Creo and it was in meters, changed back to Mathcad and the units changed to meters.
Correct. So I believe I mentioned this during the webcast, but Mathcad has, go ahead and calculate this again so we can get rid of all the errors. Mathcad has a base unit system. So right now, I think for all of them, I switched over to the SI system. So we were passing meters back and forth. For length units, we're always going to pass either meters or feet, depending on what unit system you're in. And anything we get back from Creo, even if it is evaluated in millimeters, when we come back, it's going to come back in meters. So you saw that. Where was it? Up here. Even though when I took the measurement, that Creo part is, the template of the Creo part is in millimeters, when I pull it back, it's going to come back to the default Mathcad unit system of meters. If I were to switch that to the US system and redo that, that would have come back in feet. But the conversion's done correctly for you.
Okay, next question is, can a Creo user remove all the Mathcad parameters if required?
Yep. So if I come up to the tab and hit Remove Worksheet, it's going to remove the worksheet and all the parameters associated with it. So I could click Yes, and now that's gone. No more link there. Or simply on the Mathcad side, what you can do is you can delete regions here, and that untags them, and you could save and push back. So if you still wanted to keep the Mathcad sheet embedded, but you wanted to get rid of the data passing, you can just use the table here and do the red X's like I showed. So two options.
Okay, Tim, last question here. Any questions that we didn't get to today, we will email out answers for that. So the last question is, what is your recommendation for an entry-level course for Mathcad Prime 3.1?
The one that you guys showed there, you guys had an upcoming course on the Mathcad Essentials. I believe you had said it was a 3.0 course, but it's 3.1 is from a user's point of view is really, with the release of 3.1, we introduced an API which allows this integration to be possible. So that training that you showed, that Mathcad Prime 3.0 Essentials course, will walk you through how to do, the natural math notation, the solve blocks. I believe it does programming also. So it's just, it's a 2-day course that'll teach you all the basics of Mathcad itself. And Mathcad Prime 3.0 and 3.1, if you learn one, you know the other. They're very, very similar. You honestly won't notice a difference from the UI point of view at all.
Okay, great. I also wanted to point out that if that PTC also offers e-learning libraries. So if anyone has any interest with that, please contact me. My name's Joe Ferret once again, and my contact information is up there on the screen. So if you're not able to make a classroom training, we do have e-learning libraries as well. And thank you once again, and this will end our presentation for today.
Thank you.
Thanks, Tim.